primarily going to use conservation of momentum to describe collisions of isolated objects. So we'll recall the definition of momentum, which is the mass of an object times its velocity. Because velocity is a vector, momentum is a vector too. It has direction. Conservation means that a quantity of a system is the same before as it is after. So if we talk about the system, momentum initial is equal to momentum final. Now we're mostly going to do collisions of two objects, so we can expand on that and say that the initial momentum is the momentum of object 1 initial plus the momentum of object 2 initial, and that's going to equal the sum of their momentum after the collision. If we make it one-dimensional, then the direction of the vector just becomes whether the momentum is going to be positive or negative. So we can drop the vector signs and then replace each p, each momentum variable, with the mass of the object times its velocity, whether it's in the initial velocity or the final velocity. So one example of collisions is called an elastic collision. So in an elastic collision, momentum is conserved, which is always the case, right? So we have that equation that we just defined. But the special thing about elastic collisions is that kinetic energy is also conserved. So a common example as shown here is with billiard balls, right? So billiard balls don't lose, we can say that they lose zero energy in the collision, right? So we also have this equation which represents the kinetic energy of each object before the collision, summed together is equal to the kinetic energies after the collision added together. Now with these two equations, if we know the masses of the objects and their initial velocities, we have two things that we don't know, the final velocities, and we have two equations. So in principle, we can solve this. But the algebra gets pretty messy, especially if both objects are moving initially. So we're going to look at some specific examples where we can get an idea of how objects move after an elastic collision. The other type of collision is an inelastic collision. So we still have momentum conservation. That's always true in an isolated collision. But we do not have kinetic energy conservation, right? So that energy has to go to something else. So if we look at the car crash, we can see that in that collision, some of the energy goes into deforming the objects. You might compress a spring that doesn't rebound, or some of the energy might be lost to sound. So in order to solve this, because we only have one equation and two final velocities to solve for, we're going to need some additional information. So for instance, if you're given one of the final velocities, you can figure out the final velocity of the other object. The other way we might have additional information is if the collision is perfectly inelastic. So in perfectly inelastic collisions, the objects are stuck together after the final collision, or after the collision. So they have the same final velocity, right? So that's illustrated by this football tackle, assuming that the defending player can hang on. So there's some momentum before the collision, and then the tackler wants to collide with the player who's running and hang on to them, and so that's going to lose some of the kinetic energy is going to be dissipated. So because we have two isolated interacting objects, momentum is still conserved as always. And things often start from rest. So we have, in that case, the total momentum is zero, because if both objects start at rest, then the initial momentum is zero. Right, so if we plug that in for the initial momentum on the left-hand side, we can see that the only way to get two things to add up to zero is if one of them is positive and one of them is negative. So the objects are going to move in opposite directions. And in an explosion, we're always going to end up with more kinetic energy than we started with because you had some energy that was put into the system by the explosion. So we can illustrate this with a cannon, the recoil. Right? When the cannon fires the shell moves forward, but to conserve momentum, the cannon also has to move backward. Right? So we see that the cannon rolls back. Now the cannon is more massive, so it's not going to move as fast as the cannon shell. So now let's look at some examples of uh, a more abstract explosion with the cart explosions.